All right, the sample median is the middle outcome from a data set. So the height of 9 randomly selected MNU students is in centimeters, just because that's easier than feet and inches. This is in order already from least to greatest, right? If this data set was not in order, we would have to go through the painstaking process of slowly putting it in order from least to greatest. And then, what's my sample median?
You said median?
The median's in the middle. That is my sample median. So this is a descriptive statistic. It's a way of summarizing data. And this is also what we would call a measure of central tendency, because it's kind of indicating where the center of my distribution might lie, somewhere close to 174 centimeters. The annual salaries of 8 randomly selected MNU graduates are, in thousands of dollars, $72,000, $39,000, $28,000, $105,000, $96,000, and so on. Find the sample median. So again, like I said, now that this is not provided in order, then on a test, I expect you to put it in order. That's it. Yeah. Okay. And then what's my sample median?
Like 63.5.
Yeah. Very good. So again, I can get rid of the top one and the bottom one and the second to the top and the second to bottom and the third from the top and the third from the bottom. And then I'm left with 2 because I had an even size of sample. Right, there's 8 measurements in my sample. And so then to get the median, we add the middle 2 and divide by 2 to get the midpoint, which is what's that difference? I can't do it in my head. It's 17. What's half of 17? Half of 17 is like 8.5. So yeah, you're right. It would be 63.5 thousand. All right. Pretty easy, right? New vocabulary word, expected value. The expected value is the mean of the possible values a random variable can take, weighted by the probability of those outcomes. That's kind of abstract, but I'll try to explain what I mean through examples. You consider purchasing a lottery ticket. Each lottery ticket costs $2. They're going to sell 10,000 tickets before selecting a winner, and the winner is going to receive a $15,000 cash prize. That's how this lottery is going to work. So when it says what is the expected value of this lottery ticket, we have to consider that out of these 10,000 total tickets, one is worth $15,000. 9,999 are worth $0. So whenever I say the words weighted by the probability, what I mean is the probability here of getting this outcome is 1 in 10,000. The probability of getting this outcome is 9,999 out of 10,000. So to calculate my expected value, I'm going to take a mean of the possible values that my random variable can take. So the mean would be like the average between $15,000 and $0, but this is not just a plain old arithmetic average. This is weighted by the probabilities, and so we multiply each one of the outcomes times the probability. So in the end, what's my expected value? I forgot my popsicle sticks. Hunter, what's my expected value? Cade, what's my expected value?
I even do it on my phone. I don't know the functions.
Wouldn't it be like $1.5?
$1.5. Very good. So obviously 0 times anything is 0. Don't even have to worry about adding the 0. But 15,000 divided by 10,000 is 1.5. So this is kind of the way that most gambling works, is that whoever is, running the show, the casino or the state selling lottery tickets, they're only going to sell you a ticket that costs more than the expected value of the ticket. Obviously, you win some, you lose some, but in general, the expected value of gambling is always less than the cost of gambling. Otherwise, the company couldn't make any money. Or the state couldn't raise any money for education. I don't know if Kansas does a lottery. Texas does a Texas state lottery. Does Kansas do a lottery? Yeah? Okay. Yeah, they always said the proceeds of the Texas lottery went to public education. I don't know if it's the same here, but... All right. The expected value is, like I said, the mean of the possible random values. Here's a different situation. Alice tells Bob that she will let him roll a 6-sided die. And if he rolls a 1, she's going to give him $1. If he rolls a 2, she's going to give him $2. If he rolls a 3, he gets $3, and so on. What's the expected value? So my expected value is going to be a weighted average of every outcome. And one outcome is $1. The weight is the probability. What's the probability that I get $1? 1 out of 6. I could also get $2. What's the probability that I get $2? 1 out of 6. Yep, and that's how it goes, is they're all a 1/6 probability of rolling a 1, 2, 3, 4, 5, or 6. So in this game, what is the expected value of rolling a die? What do you get, Ray?
3.5.
Very good. The expected value of rolling a die in this game is $3.5. So, expected value is by happenstance just the median in this probability distribution, but that's just coincidence. That's not always the case. Like in this distribution, the median is really $0, right? The middle outcome is still 0. So the expected value isn't always the median for a probability distribution. And so they're kind of communicating different things. The median is like more often the typical outcome that you might expect from a random variable, whereas the expected value is more like, okay, what if I repeat this experiment or I repeat this random process like 1,000,000 times? What's going to be the overall effect? That's why it's an average. Okay, the sample mean is the average of the outcomes from a data set. So if you have something like this, the height of 9 randomly selected MNU students, and I ask you on the test to find the sample mean, here's the quickest and easiest way to do this. If you haven't already, you should really download that Desmos Test Mode app on your phone, because when you get to this, you don't have to pull out your calculator and type in 168 plus 169 plus 172 plus 173 and so on. What you should do in Desmos Test Mode is name a list A or something like that. So you type in lowercase a equals open bracket, little square bracket. And when you open the square bracket, Desmos knows that I'm about to type a list of numbers, and I type it just like I'm showing you in my notes, where I'm going to separate each number with a comma. So I'm going to type in 168, comma, 169, comma, 172, comma, 173, and so on. And it's always a good idea. Desmos is going to tell me how many elements are in your list, just to go back and double check that we have the same number of elements. That means I didn't miss any commas anywhere, It would really mess this up if you accidentally mistype something, like you get digits out of order, right? Now, what if I want the sample mean? I could go to the button here, and on your Desmos Test Mode app, I think it just says FUNC, func. And so you click func for functions and scroll down to statistics, and we're going to select mean. And it turns out there's even a median button if you really need help finding the median. But you can just click mean, and then inside the parentheses next to mean, we're just going to type the letter A to tell it to look in my A list to calculate the sample mean. So that's super easy. You can add them all up and you can divide by 9 to get the sample mean, or you can just do this, and it's.
For that one, what do you have to type in the order if they're least to greatest?
Not for the sample mean. And in fact, not even for the median, because it'll reorder it automatically when it finds the median for you. Yeah.
Does it reorganize it just kind of for itself, or does it physically reorganize it?
Just inside the calculation. Yeah. Yeah. So let's make this out of order for fun, I guess. Let's put the 168 at the end and see what happens. So obviously the mean stays the same. And then it'll still give you the right median. It'll still tell you the median is 174, even though my list is out of order. Okay. So that's how you do means. That's how you do sample mean in Desmos. Remember, this capital Greek letter sigma is telling you to add everything up. So the X with the little overbar, that represents the sample mean. This symbol is telling you to take the sample mean. And the capital Greek letter sigma means add up all of the stuff that looks like this, where the little X subscript K is talking about the individual measurements. So it's saying add up all the individual measurements and then divide by n, where n is the number of measurements in your sample. N is the sample size. Okay. So I already kind of mentioned some of this. The sample median is the middle of your data set. One reason you might want to use the sample median as your measure of central tendency is because the median automatically filters out outliers. Outliers are a little bit hard to describe. It's more of a qualitative definition rather than a formal, rigorous definition right now. If I have some data set with measurements all right here, and then I take another measurement and it's way over here, this one doesn't fit in with the rest of the set. It's much larger, let's say, along a number line from left to right. And so this might be an outlier. If everybody on my basketball team is between like 5'6" and 6 foot tall, but I have one, just massive freak that's sitting at like 7'2", he would be an outlier. He wouldn't fit in with the rest of the measurements. I'm talking about the height of my basketball players. So why do I care about filtering outliers? Well, maybe I want a measure of the central tendency of my probability distribution that doesn't take into account people who have just extreme measurements. For this reason, a lot of times you will see median household income reported as like a demographic of an area. Like if I were really interested, I could go online and search like Overland Park, median household income. And it'll tell me, if I was going to sort all of the households in Overland Park from like least to greatest total household income, and I find the one that's in the middle, it should be pretty close to $104,000. This is better than taking an average household income, because I'm sure there's some people in Overland Park that might make like $100 million a year. But that's such a strange outlier. It in no way reflects the typical demographic of the population. And if I really care about how the local economy is doing, I'm not really interested in those weird outliers. I'm more interested in the typical household. So that's why when you use medians, it's because it automatically filters outliers, just because we're choosing the middle data point and the other data points don't even matter. Okay, sample mean is obviously the average. Interesting enough, we were talking about expected value. If you take a sample mean of the data you get from a random variable, that's the best possible approximation of the expected value. So we don't actually know the expected value most of the time. The two examples I gave were for gambling because it's easy to calculate probabilities for gambling. But in like a real life situation, we don't typically know the expected value of a probability distribution. That's a parameter. That's something we can't know exactly, but we can approximate it using the sample mean. So that's one reason the sample mean is useful. And like I said, if you want to know what's the overall effect of repeating an experiment many times, then the sample mean would be more useful. Like if you are a baseball coach, they do batting averages because your player is going to go to bat many times during his employment with the Royals or whatever, right? You care what's the overall effect of many out at bats. Or if I have, let's say, a part of a machine, like let's say you're responsible for the maintenance of the trash trucks in Olathe, and the trash trucks are driving around all day long. They have to replace their brake pads all the time. And in the life of a trash truck, which might be like 30, 40 years, you're going to replace the brake pads every year. So you're going to replace this part over and over and over again. What you would really care about is the average lifespan of the brake pad, not the median, because you're going to repeat this process. And that's more useful to you. So there's some situations where the median is important. There's some situations where the sample mean is more important. An outlier, like we said, is a measurement or outcome with excessively large deviation from the others. Descriptive statistics are numbers that summarize data or describe a sample, like sample mean, sample median are both examples of descriptive statistics. There's a lot of others that we'll talk about today. We're not talking about this today, but later in this class we'll talk about inferential statistics. Inferential statistics are numbers that summarize what we know about a population. So inferential means we're making an inference. We're looking at just the sample. We're looking at just our measurement, our data set, but we use the data set to make an inference about the population itself. So we're not going to talk about that today because that involves a lot of probability theory to get there. But we will, by the end of the semester, discuss inferential statistics. Parameters are numbers that are innate to a population or a random process. In most cases, we can never know a parameter's true value, but we can approximate it with descriptive statistics.
So is that, because we talked about parameters, I think, second lesson.
Mm-hmm.
Are those the same?
Yep, it's the same term. I probably just put it in my lecture notes twice, but it's the same thing. I'm still talking about the same parameter. So the population mean is also known as the expected value. That means the same thing. Expected value is a parameter, and it means exactly the same thing as population mean. Those are synonyms. And the symbol that we use to represent population mean is a lowercase Greek letter mu. The sample mean is the best approximation of the population mean. Because the population mean is a parameter, we almost never know what the parameter is in real life, but we calculate a descriptive statistic to approximate what that parameter would be. Likewise, the population median is a lot of times denoted with a mu with a little tilde on top for the median. We almost never know what the median is for a population, but we can approximate the population median with a descriptive statistic called the sample median. And this is the strangest thing because even though population mode is a real thing that it exists, like the most likely outcome from a probability distribution is called the population mode. And the way you would estimate this for a discrete distribution is with the sample mode. Only I've looked in a bunch of different textbooks and nobody actually uses any kind of symbols for this. I would have expected like a Greek letter here, or some kind of way to denote the sample mode, population mode, but they don't exist. I don't know why there's no notation. But again, the sample mode would be a way to approximate what the population mode might be. The sample variance is a way to approximate the population variance. We'll talk about variance here in a minute. And the sample standard deviation is a way to approximate the population standard deviation. So I don't remember if we said this. Down here, this is a lowercase Greek letter sigma. And we use the lowercase sigma to represent the population standard deviation. And since the variance is always just the standard deviation squared, we don't have a separate symbol for variance. We just write sigma squared to represent variance. That way you can't ever forget the relationship between those two. And then for sample variance and for sample standard deviation, we use the English letters. Basically, English letters means descriptive statistic, Greek letter means parameter. All right, new vocabulary word, resilient. We say that a measure of central tendency is resilient if outliers don't really affect it much. So these are our three measures of central tendency. If you see the term measures of central tendency, that means sample mean, sample median, sample mode. Those are my measures of central tendency. And from most to least resilient, I would say that the sample mode is the most resilient. And the sample mean is the least resilient. I'm going to take my own advice and create a little spreadsheet here. I'm going to come up with some random values that are going to have a mean of 50 and a standard deviation of 10, let's say. Okay. And from this, I'm going to calculate a sample mean, a sample median, and sample mode. Oh yeah, there's not a mode, is there? Because this is a continuous random variable, the way I made these numbers. And a mode only really makes sense if it's a discrete random variable so that you can have the same outcome appear more than once. So I guess if I actually want to do this, I better come up with a discrete random variable. And I could do that just by making these numbers round to the nearest integer. And yeah. Oops. Try that again. That's funny, there's actually two modes that showed up. I've got 54 appearing twice, I've got 60 appearing twice. So let me make this one a 59. That way I've only got one mode. So now my sample mean is 53.57, my sample median is 54, my sample mode is 54. Let's see what happens if I add an outlier, like the number 999. We'll do before and after. This is before. And then let me add 9999 to it. This is after. So when I added this little outlier to my data set, the mean jumped up from 53.5 all the way up to 172. So that got affected a lot. What about the median? Well, the median did get affected. Not very much, but it moved from a 54 to a 55.5. So again, the median kind of filters out outliers. The first thing it does when you find the median is you scratch off the smallest and largest numbers. But the mode stays exactly the same. The mode does not care about outliers whatsoever. So we say the mode is the most resilient then. The mean is the least resilient measure of central tendency, and the median is pretty dang resilient. Okay. Those are all of our measures of central tendency we're worried about in this class. So let's talk about dispersion. Dispersion is a word that refers to how much a data set is spread out. Which data set? This one on the left, we'll call it data set A. Or this one on the right, we'll call it data set B. Which one has more dispersion? What'd you say? B. Yeah, I'd say this B is more spread out. And there's several different ways we can put a number on this, like how spread out is the data. We're going to talk about 4 of them in this class. For one thing, we can do the range, which is the maximum minus the minimum. Sample variance and sample standard deviation are 2 measures of dispersion, telling me how spread out my data is. And then also the last thing is IQR. That stands for interquartile range. We'll talk about that as well, so that we have 4 ways to measure dispersion. So there'll be 4 descriptive statistics. And like I said, if I was comparing how dispersed these are, one thing I could do is the range. Range is just the maximum from my sample minus the minimum. So here is the range, and here is the range, right? This is clearly a larger range because it's more dispersed. Okay, new question. Caitlin. This is A, this is B. Does A have a larger range than B? No? Do they have the same range?
They have the same maximum and minimum.
Yes, they have the same max and min, right? So they have the same range. But Martina, would you say that set A and set B have the same amount of dispersion? No. Are they just as equally dispersed? Which one looks more dispersed? B. Yeah, B still looks more dispersed. And that tells me that range isn't a very good measure of dispersion. I would like a measure of dispersion that can tell me the difference between set A and set B, because B does look like it has more dispersion to it. So range isn't going to work very well. What I would like to do instead is not just consider 2 points, not just consider the maximum and the minimum, but also consider the deviation of each and every single point of the whole data set, not just the min and max. The deviation of a point is the difference between that point and the sample mean. In other words, deviation of a measurement is the measurement minus the sample mean. How far does it deviate away from the sample mean? So one thing we could try is say, what if we just add up all of the deviations? Remember that capital Greek letter sigma says add up all of these deviations for every measurement. That could be a good thing. If we were to do this, remember that adding and subtracting are associative, which means I don't really need the parentheses if all I'm doing is adding and subtracting, right? We can get rid of the parentheses. Also, adding is commutative. I can commute terms in a big sum. I can move them in whatever order I want. And so as I'm adding up n different measurements, if n is my sample size, this would be equivalent to saying, let me take the sum of these n different measurements And instead of adding up their dispersion, add up the measurements and then subtract n times the sample mean. Right? Because I was subtracting the sample mean n times here in this sum, and this way I'm just taking away the parentheses and commuting all of those. So I have n copies of the sample mean I'm subtracting here. Well, what happens if I write it like this? N times 1 divided by n is just the number 1, right? And I can multiply by 1. Multiplying by 1 doesn't change the value of anything. But what is the sum of all the measurements divided by n? That's the mean. Let me draw your attention to that. This right here, when I add up all the measurements and divide by n, that's the same thing as the sample mean. So I've got n times the sample mean minus n times the sample mean. That's always going to be equal to 0. If I calculate the deviation for every measurement and then add them all up, it always gives me a 0. So that's not a very good measure of dispersion. If every data set always has a 0, that's not telling me anything at all. So adding up the deviations is not going to work. It's always going to give me a 0. Instead, what I could do is calculate the absolute value of the deviations. So that way, all of the deviations are going to be made into positive numbers. And then when I add up all of the positive numbers, it can't be 0. It's got to be a positive number. Or the other thing I could do is I could square it. Because if I take a positive number and square it, it becomes a positive number. And if I take a negative number and I square it, it also makes a positive number. Oh, so I could do that instead. Take these squared deviations. And this is what we're going to do. Now, maybe some of you are thinking that feels like really unnatural. Like if we could just take the absolute values of the deviations, isn't that just simpler, easier, better? This is not a mathematical statistics class. This is a baby's first intro to statistics class. So we're not going to dive into the big full proof of why we do this. But there is a really, really good mathematical reason why we want to use squared deviations instead of absolute value deviations. It's just not one of the things we're going to discuss. But squared deviations turn out so much nicer in the math, and there really is a good motivating reason to do this. If you're interested, sign up for my class, Probability Theory, when it's offered in the next couple of years. So we're going to use squared deviations and add those up instead. When we add up all of the squared deviations, this gives us a measurement or a measure of dispersion called the sum of squares total, SST. Sum of squares, because they're squared deviations. So if you see the acronym SST, that's what we're talking about. And this is doing good because it's taking every deviation into account. It's not 0, it's a positive number. And like I said, there's a real motivating reason we're squaring things. For one, this is something that you probably could understand, is like whenever you square something, it makes a parabola curve instead of just a straight line like the absolute value would. And so a larger deviation gets punished more, right? Like you end up adding more to the SST when you have a larger deviation because it's squaring itself, it's growing faster. So this, in a way, punishes outliers more so than the absolute values would. But this is still not a perfect measure of dispersion because with SST, the more measurements that I make, the larger the SST becomes. You notice that every single time I add a measurement, I'm adding some squared deviation, and so it's always going to become larger every time I make a measurement. And so I don't like that. I don't like the idea that just taking 1,000 measurements is going to give me a huge measure of dispersion. And so one idea is, what if I take the average squared deviation? We could just divide by n, get SST divided by n. And again, this is one of those things where I wish we could talk about it, but we just don't have time in an intro class. This is almost perfect, but it remains slightly biased. It's a tough explanation to really sell it why this would be a biased estimator, but it's not quite a perfect estimator of population variance. Instead, what we need is to divide it by n minus 1. Because dividing by n minus 1 removes that bias I was talking about. So that sample variance is an unbiased estimator of population variance. And again, I wish I had a better explanation for you today, but it's just a different discussion for a different class. We always divide by n minus 1 for the sample variance. And then, like I told you earlier, the variance is just the sample standard deviation squared. That means, conversely, the sample standard deviation is just the square root of the variance. These are our best measures of dispersion that we have in statistics. The best way to tell you how dispersed a data set is by telling you the sample standard deviation. Exercise 6 says, calculate the sample variance and the sample standard deviation for this sample of lizard lengths. Now, the first step is the deviation of every measurement. So to calculate deviation, I'm going to need to calculate the sample mean.
Would you order them in order to least to greatest first?
I could, if I wanted to, I could. That's fine. It doesn't really matter for means, and it doesn't really matter for variance or standard deviation. So the sample mean is 1 over n times the sum of all of my measurements. So in other words, it's going to be 1 divided by 4 times the sum 15 plus 13 plus 18 plus 14. And remember, on a test, you could do this in Desmos to save time. I'm just illustrating how this would go in if you had to use the formulas. So this is my sample mean. It's 15. Then for the deviations, x1 minus x bar would be 15 minus 15, which would be 0. x2 minus x bar would be 13 minus 15, which is negative 2. x3 minus x bar is 18 minus 15, which is 3. And then x4 minus x bar would be 14 minus 15, which is negative 1. What we are doing when I calculate the sample variance is I say the sample variance, it's supposed to be an S, is going to be the sum of squared deviations divided by n minus 1. So let's take the squared deviations.
So wait, would you square all of those deviants before adding them all up?
Yes.
Okay.
Yep. So 0 squared is 0. Negative 2 squared is 4. What's 3 squared? 9. And negative 1 squared?
1.
Positive 1. Yeah. So then my sum of squares total is 0 plus 4 plus 9 plus 1, 14. And then n is 4, right? So n minus 1 is 3. 14 over 3. Whatever that is. Yeah. Yeah. With 4 significant figures, that would be 4.667. This is the sample variance. Now, if we were being really careful engineers and we were keeping track of our unit of measurements, all of these are given in centimeters. This is 15 centimeters, 13 centimeters, 18 centimeters, 14 centimeters. So the sample mean is in centimeters, because I'm adding up a bunch of measurements in centimeters and then dividing by 4. The deviations are deviations measured in centimeters, because I'm subtracting 1 centimeter minus another centimeter. The squared deviations would then be centimeters squared. That's no longer a measure of length, but this is a measure of area. Kind of weird. Then when I add those together, I'm still talking about centimeters squared. Adding up a bunch of areas would give me an area. And then over here, whenever I divide by the number 3, because there was 4 measurements and I divide by n minus 1, then I'm going to get a number with units of centimeters squared. So the sample variance is an area. Even though my measurements that I was originally taking were in length, I've got a bunch of measurements in length, the variance that I'm telling you about to measure my dispersion is an area. And that's weird. That's unnatural. It doesn't feel right. So the reason that we calculate sample standard deviation instead of just variance is because it's going to give us back the same unit of measure that we started with. When I take the square root of the variance, we need the square root of 4.667. 2.160, rounded to 4 sig figs. And this is in centimeters, because we just took the square root of an area, and so that gives me a length again.
So is there any situation that you would use just simply sample variance, or would you always want to calculate them both? Like, what's the point of sample variance?
In this class, no. I think in this class, what really matters is the standard deviation.
So in this class, sample variation is kind of pointless.
You mean variance?
Yeah, sample variance.
Yeah. I mean, you do calculate the variance on the way to calculate the standard deviation.
It's just like an extra step.
So it's just, yeah, just one of the steps. Yeah.
Makes sense.
Yeah, I mean, I understand that most people are not going to continue to take additional statistics classes after this, but if you were going down that route, you would learn in future statistics classes why variance does matter. It's not completely useless, but it's just not something we're going to focus on in this class. Okay, moving on. The 5-number summary is a way to describe a data set. And there are 5 numbers in the 5-number summary. They go sample minimum, sample first quartile, sample median, sample third quartile, and sample maximum. Now, I'm sure you can imagine what the sample minimum and sample maximum are. Those are the smallest and biggest numbers you see in the sample. The median is the median like we talked about. The first quartile and the third quartile are the new elements of the 5-number summary. And to get those, you treat the first quartile as the median of the lower half of your data set when you put it in order. And you treat the third quartile as the median of the upper half of the data set when it's ordered from least to greatest. Then we talked about one more measure of dispersion. It's the interquartile range, or IQR. And the interquartile range is just the difference between your quartiles. You subtract Q3 minus Q1, and you get the IQR. We'll do an example. We'll do at least one example. Exercise 7 says, find the 5-number summary of the data set, then find its IQR. So first, order the set from least to greatest. And very conveniently, we've already ordered this set of numbers from least to greatest. How many numbers do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means I can find the minimum very easily. I can find the maximum very easily. The median should be number 6. 1, 2, 3, 4, 5, 6. This should be my median. And then to find the first quartile, we could take the lower half of the data set and then find the median. What would be the median of the lower half? 9.5. 9.5. And to find the third quartile, I'm going to look at the upper half of my data set. What's the median of these numbers? In green. 18.5, yeah. So that's the third quartile. So altogether, my 5-number summary would look like this. 4, 9.5, 11, 18.5, and 21. That way I've got the minimum, the first quartile, the median, the third quartile, and the maximum all written in a row. Now, everybody is dying to raise their hand and ask the question like, do we always include the median? And the answer is, it's up to you whether or not you want to include the median. This is technically called the first quartile inclusive because it includes the median. And this would be the third quartile inclusive because it includes the median. What would be the third quartile exclusive? Yeah, if I exclude the median, then the third quartile becomes 19. And if I were to take the first quartile exclusive, what would be the first quartile? 9.
So then, will you specify on a test whether you want it inclusive or exclusive, or do we have to specify it?
On a test, I might specify inclusive or exclusive, or if I don't, I'll take either one to be the correct answer. I'm not going to count off points if you give me one or the other. I honestly don't care that much. I mention this out loud because I know that Pearson on the homework assignments will tell you to take the quartiles inclusive or exclusive, and I want you to know what that means. And if you're using Microsoft Excel, and you want to know what the quartiles are, let's take the quartile inclusive, or the first quartile. We're going to type in the word quartile, and then it's super duper tiny, and I wish there was a way to make this larger, but the first option is quartile.exc for exclusive, and then the second option is quartile.inc for inclusive. So if I type .inc, and then I select my data set, and then I tell it which quartile I want, that's my first quartile inclusive. Here's my first quartile exclusive. I just have to type in .exc and select my data set and tell it 1, and you can tell that there's a difference. So if you're using Excel or you're using some other software to do your statistics for you, a lot of times it's going to ask you, do you want your quartiles inclusive or exclusive? And it doesn't matter. I don't think it matters at all personally, but maybe it does. I don't know. Never run into a place where it matters. Now the next thing is IQR, interquartile range. The interquartile range is just the third quartile minus the first one. And so if I look at the inclusive IQR, that would be 18.5 minus 9.5. That'd be 9. And if I were to use the exclusive quartiles, that would be 10. Very tiny differences in the way that you choose to calculate those quartiles. Because I'm a lazy person, I normally do this. I normally will choose the exclusive quartile in this case, because then there's an odd number, and I can pick the middle. And likewise over here, I'd have 5 numbers, and I could just pick the middle. But if I had 13 numbers instead of 11 numbers, I would choose the inclusive quartiles, because that way I would have an odd number, and I could just pick the middle number.
You mean 12? You said 13.
No, I meant 13. Right?
No, because then it would be an odd
I don't know, because then it would be... Yeah, so I said, no, I was right. Listen to me again. In this case, I would rather use the exclusive, because I would have 5, 1, and 5, right? So I'd have 5 and pick the middle one. If I had 13, it would be 6, 1, and 6. So exclusive would give me an even number. But if I do inclusive quartiles with 13 as my sample size, I pick the middle out of 7.
Okay, I get that.
Yeah. It's okay. I'm talking way too much about inclusive and exclusive quartiles. I'm probably just confusing everyone at this point. The percentile is another way of summarizing large data sets. This is the part where we actually do need the Desmos test mode. So get that ready momentarily. Suppose 3 million high school students took the PSAT college entrance exam, sort the scores from highest to lowest. 10% of 3 million students is 300,000 students. And so if I were to find the student who is ranked number 300,000, that student's PSAT score is the 90th percentile. So big score means big percentile. If you are the 99th percentile, you have almost the top score. Okay? Give you another example. In the United States, we have 328 million residents. So 1% of the US population would be 3,280,000 residents. If you found the person who ranked number 3,280,000, that person would say, I have the 99th percentile in wealth. Right? They're 1% away from being at the top. This is an interesting graph. But this says that in terms of family wealth, the 99th percentile was 10,400,000 in the US, whereas the median was only about 97,000. And this was 2016, so this is a really old graph. But the curve has gotten even steeper since then, over the last 10 years. So notice that these are the same. If I tell you I'm talking about the first quartile, that's the same thing as the 25th percentile, because 25% is 1/4 of 100. The median is the same thing as the second quartile, is the same thing as the 50th percentile, because second quartile, 50th percentile, that's halfway, that's the median. The third quartile is the 75th percentile. I'm not being too picky about whether I'm talking about the population or the sample, and so that's why I put the word or here. You have to use context clues to think about whether we're talking about the population or the sample. Find something to pick on. Man, I can't remember your name.
Blake.
Blake? Oh, Hunter and Blake. I was thinking you were Blake. Okay, Blake. Tell me, if you give birth and the doctor tells you your baby's weight is the 21st percentile, is your baby heavier than the median or lighter than the median? Lighter, yeah. Small percentile, small weight. The percentile goes with the size of the number, regardless of context. So sometimes it's good to be high percentile, sometimes it's bad to be high percentile. It depends on the context. Okay, this is the part where we're going to start using Desmos. The z-score, this is a vocabulary word, the z-score, follows this formula, okay? To find the z-score of a measurement, you take the measurement, subtract the population mean, and then divide by the population standard deviation. So that every single measurement in your whole sample has a z-score. It's a property of every measurement, not a property of the sample as a whole. We tend to assume that a random variable follows a normal distribution, especially if we don't explicitly specify that in a question. You could just assume it's a normal probability distribution in this class. And we're going to use Desmos test mode app to convert z-scores into percentiles. Okay, but remember this formula. Put this formula on your 8.5 by 11 notes sheet that you're going to use on your test next Tuesday. You have a 3-month-old female baby and she weighs 15 pounds. Suppose 3-month-old female baby weight is normally distributed with population mean 12.9 pounds and population standard deviation 2.2 pounds. What is your baby's percentile? So step number 1 is calculate the z-score. And our z-score is going to be our measurement minus the mean divided by the standard deviation. So that's going to be, in this case, 15 minus 12.9 divided by 2.2. And that's going to be 2.1 divided by 2.2. I don't know what that is. 0.9545. And the z-score is the number of standard deviations you are away from the mean. It's positive if you're above the mean, negative if you're below the mean. And so this baby has a z-score of 0.9545 in baby weight. Let's turn it into percentile. I'll show you how to do this, and you got to pay super close attention. If I want a percentile in Desmos, I've got to click on the Func button, F-U-N-C, Func, and then scroll down to not statistics, but actually past statistics, down to probability distributions. And the button I want to press under probability distributions is normal dist, because we've assumed our random variable is normally distributed. So we'll click on normal dist. Now, everybody's phone should look like this. Without messing with it any further, I'm going to click on the arrow cumulative probability. Pop that one down. Then I click left, and in the blank, I'm going to type in 0.9545. So let me say that again. You go to Func button, you scroll down the probability distributions, you select normal dist, you click the drop down arrow next to cumulative probability, you have to select left for the region, and then in the blank where it says the probability open parentheses x less than or equal to, that's where you type your z-score. We just calculated our z-score as 0.9545, so that's what I type in the blank. And the answer to the question, what is my baby's percentile, is this drop-down box. You might have to tap on the drop-down box on your phone, and it will tell you that the number is 0.8301. Rounded to 4 significant figures. And so I say that my percentile is 0.8301, which is the same thing as 83.01%. That's the answer to my question. That means this baby is heavier than 83.01% of babies that are female and 3 months old. And this baby is lighter than 17% of babies, or 16.99% of babies. But the Desmos part is important. You got to know how to do this on the Desmos test app for your test. One more example and I'll let you go. I know we got 2 more minutes. Suppose that IQ is normally distributed with population mean 100 and standard deviation 15. What if your IQ is 130? If you are asked for percentile, you got to do z-score first. And the z-score is your measurement minus the mean divided by the standard deviation. So we're talking about 130 minus 100 divided by 15. So the z-score is 2. You might say I'm 2 standard deviations above the mean, or you might want to know what is your percentile. And to get the percentile, you would go here, keyboard, Func, scroll down to probability distributions, select normal dist, hit that cumulative probability drop-down arrow, click left, and then you type in your z-score. We want the probability that x is less than or equal to 2, because that's my z-score, and then we click that drop-down box to get my full answer, and that is 0.9772.
So when you're writing down percentiles, how far do you want it surrounded? Like just 4?
4 significant figures. Although I guess at one point I told you that for percents like this, when you're close to 1, that the 9s don't count. And so maybe what I should write is 97725.
What if we like did add the 4, or I guess the 5? We wouldn't be able to dock points.
I don't know. I'm pretty cool when I grade tests. I probably wouldn't take off any points for that if you're off by 1 sig fig. Okay.